Good afternoon. Welcome to the Engineering and Construction webinar series. My name is Eric Mucklow with the headquarters of the U.S. Army Corps of Engineers in the Engineering and Construction Division. This is a second of our 2016 series of the webinar series for focusing on mainly energy and sustainability and also building technology and other things of interest to our ENC community. Again, this webinar is recorded and hopefully will be posted for later viewing for those that may miss it. If you'd like continuing education credits for this session, you can go onto our website, shown on the screen now, mrsi.erdc.drnen.mil/sustain, download the quiz, answer the questions, again in groups of 5, and submit it to the email at the bottom of the screen, s_e-webinar@usace.army.mil. And if you get the quiz answers correctly, we will submit for your credits. Today the session is on dynamic glass. Fairly interesting technology. This webinar will provide you with an understanding of electrochromatic dynamic glass and how it can be used as a design enabler. Studies have confirmed that the sun's daylight and a connection with the outdoors provides many benefits to the human health and natural body function. It is important for all stakeholders in the built environment to understand how effectively to use the sun for interior daylighting while preserving the view of the nature in place. Dynamic glass is a solution that synthesizes the competing ends of daylighting and views, energy efficiency, and occupant comfort. Our presenter, Christopher Allen, is the Territory Manager for SageGlass, a manufacturer of dynamic glass products. He is a former U.S. Army officer who studied at city and regional planning at the prestigious Georgia Institute of Technology, Go Jackets, class of '90, where he developed an interest in sustainable urban trends. Through St. Gobain recruitment, he discovered SageGlass, which is the world's leading supplier of electrochromatic dynamic glass. The company aims to create sustainable habits for people in the 21st century and beyond, and is gaining traction for the next frontier of glazing solutions, which is why we're here talking about the new building technology. At this time, I'll turn it over to Chris.
Okay, can everyone hear me all right? Okay, I'll take that as a yes, the audio test here. So without further ado, thank you, Eric, for the introduction, and ladies and gentlemen, thank you for having me today. What I'm going to do is I'm going to go to the beginning of the slide here, and okay. Just give me 1 minute to get oriented here. Real quick, what does everyone see on their front page? Because it looks like mine is not on the page I need it to be on.
I'm seeing an introduction to dynamic glazing.
Okay. For some reason, mine is showing up. Looks like it's the last slide. So I'm going to see if I'm going to play around with it here for a second. I do apologize, everyone. Let me get everyone on the same page here.
Oh, Kelli says she sees the room with floor-to-ceiling windows and chairs.
Okay, see, I think we're not all on the same page. I'm trying to get to the first title page here.
Yeah, maybe click on that icon with the plus on it underneath the slide and set it to show that part 1 again. Let it reload.
Okay. Okay. Eric, can you control the slides from your perspective? And if that's the case, will everyone be able to see that?
Hopefully. You can pass the presenter mode back to me with that button on the bottom.
Okay.
And then you can just say next slide.
All right.
Here it is.
Let's see if I can do it this way.
Yeah, it looks like it's working to me, but okay, I don't know.
Can everyone see the presentation on Eric's screen? Does everyone have that same page, or are we all on different pages?
Yeah, it says an introduction to dynamic glazing.
Yeah.
If you don't see that, put something in
the chat. If it's all right with you, I'll just have you be my slide changer so we can move on here.
Okay. Yeah, Kelli said that she sees the intro slide. Okay.
Okay, excellent. All right, we'll roll with this then. So next slide.
All right.
So as Eric mentioned, this is an AIA-certified presentation, and again, from that introduction, I'm Chris Allen with SageGlass, and even though we are the world's leading provider of dynamic glass, I'm going to keep this presentation brand neutral and just explain the technology. So we'll move on here. Again, if you have any questions about anything that you see in this slide, this is controlled information, so I believe my contact information should be available for the group here, and just send me an email or give me a call, and I'd be happy to send you answers to your question. All right, next slide. Okay, just to cover the learning objectives, we're going to start off by just explaining what electrochromic is, how it works, and explain how it simultaneously achieves the balance for the competing ends of energy performance, daylight views, and the human comfort. We're going to look at the aesthetics of electrochromic glass, both from the interior and exterior perspective, and then we're going to look at the other human factors, the benefits associated with electrochromic glazing. We're going to really look in and see how it can meet that optimal energy performance need. And then finally, we're going to talk about zoning, which is an important concept if we're going to employ electrochromic glass effectively. All right, next slide. Okay, a good place to start, back to the beginning of our records of human civilization. We've got this quote here: "Ever since the first cave people crept indoors for safety, humans have sought to bring sunlight in from the outside." So we can see from records of anthropology, we can see how humans have evolved over time. And so starting at some of our earliest civilizations, the challenge has been for people to seek shelter from the indoors. But with that comes a problem about how do you light interior spaces. So obviously, with the first cave people, there was interior fires being built. As you fast forward throughout the progression of technology, as urban trends evolve, we're able to build bigger and larger urban systems. And with improvements in building construction technology, we can build larger and larger buildings. If you fast forward all the way to the end of the 19th century, we're finally able to improve electricity, and through Edison and Tesla and Westinghouse, we're able to bring the electrical lighting into the interiors, which is a revolution. Now we're able to illuminate interior spaces through electricity. Building trends change even further. As you move into the early 20th century, we're building large tenement houses with large air shafts to bring in light and air. But you can see that we're constantly trying to answer this question of how do we effectively light interior spaces. And as we move into the mid-20th century, into the 60s and 70s, we're able to build really deep inset buildings with really deep recessed footprints with a lot of fluorescent lighting. And just as many things do, tastes and preferences change over time. And what we're seeing today is a real reliance on solar energy and daylighting to light our interior spaces. So that's where we're really moving towards. And we'll go ahead and go to the next slide. As we talk about the sun, this is a very helpful quote here, that daylight is a drug and nature is its dispensing physician. And what we mean by that is we as people have evolved over the years to require the right amount of sunlight at the right amount of time in order to have our bodies perform optimally. And specifically, we're talking about the circadian rhythm. And we know that when we're not exposed to the sun, there's detrimental effects to our health. We see imbalances with hormones. We see a lack of that sleep-rest cycle. And there's a host of other health issues associated with lack of exposure to sunlight. So this is really gaining a lot of traction. And as we move forward here, as architects and designers and planners, it seems like a simple problem. We can go to the next slide here. If we just put up a bunch of glass, then we can go ahead and say that our buildings are daylit. But we know that it's not quite that simple. Even though the sun has a lot of benefits to people, we know that it has two additional problems. With solar energy, you have heat and glare. So slide, you can see a situation that may be familiar to you here. So I can certainly relate to this. Going to school as a student and having that sun hit me just right around 11:30, and whatever benefit I was getting from that natural daylight is completely counteracted with the heat and glare condition. So this is obviously something that I think many of us can relate to here. So as we go to the next slide, you can see some of the solutions that we have. Obviously shades, blinds, and as we move forward, you can see a scene that looks something similar to this. So as architects and designers and planners, this isn't exactly what we want the exterior of our building to look like, but I think it's interesting just to take this picture in for a minute. What you see here is an interesting social phenomenon where people who have control over their blinds, and shades in this case, when they have a glare condition or a heat problem, they'll pull those shades down. And when that glare condition has moved, some people will move the shades back up or adjust them at a height that's appropriate, and some may not. So what you have is when people have direct control over their blinds and shades, you have a real lack of uniformity, which can really affect the aesthetics of the building. So again, as we move on here, I want to drive home this point with this little Venn diagram here with these three competing goals and where dynamic glass falls into. So starting at the bottom right, you've got daylighting and views. And we've already established that daylighting is important. First of all, the sun provides us with essentially free solar energy that we can either choose to work with or work against. But it's also important to mention the concept of views. And I don't know if anyone here got a chance to go to Greenfield this past November, but one thing that I learned that is a concept that's catching a lot of steam is the concept of biophilia, where essentially it means just a love of nature or a love of the ecology. And it's a trend that's really gaining a lot of traction, where we plan green spaces and trees and ecology into the built environment so that from the experience inside, we actually get to see the green space and the ecology, and it gives us, it accomplishes two things. The first thing it accomplishes is it connects us to the outdoors. It gives us that almost that evolutionary sense that we have to be connected to nature. But because we're indoors, we know that we're secure and we're safe from the elements or whatever threats are out there. The end result is that we feel more connected to nature and we feel more secure. So that's, again, that's something that's starting to gain a lot of traction. The second one here is low energy consumption. And the idea is that we want, as I mentioned before, we can either choose to work against the sun or work with the sun, either a passive or a more aggressive sort of approach with the sun. In this case, we're talking about too much heat gain or loss, inadequate solar control, or proper daylight harvesting. And then finally, you've got the occupant thermal and visual comfort. And this is essentially the most important part is whenever we plan for the built environment, be it small or large, we want to always consider what is the experience of the end user. So in this case, we're talking about heat and glare as the two main points that we're trying to control for. And as we move forward to the next slide, you can see that dynamic glass is essentially the solution that achieves all three of those competing goals simultaneously. So we're going to dive a little bit deeper into what that means. As we move forward, I'm going to orient you to this graph here. So just to show you, on the y-axis here, and this is the low-res version, but in the high-res version, it's a little bit easier to understand, but I think we'll be good here. In the y-axis, you've got the solar heat gain coefficient, which essentially is a measure of the amount of solar heat coming through with this specific glazing product. On the x-axis, you have the visible light transmission, which, as we all know, if you are standing outside and there's nothing obstructing between you and the sun, you're going to have 100% visible light transmission coming at you. Anytime you put any sort of substrate or glass between you and the sun, you're going to get a diminished percentage of visible light transmission. So anytime light is coming through a surface, it's going to have a 4% reduction in that visible light transmission at each surface that it hits, and that just happens through the dispersal of light. So in this example, I'm giving you just a sample of the double pane glass products that are out there, and you'll notice that there's a trade-off between visible light transmission and solar heat gain. You can see a loose correlation there. The idea is that if you want the clearest glass products available, you're going to be in the high end of that visible light transmission. But the trade-off is that you typically have a higher solar heat gain coefficient with that. So on the high end, in this case, we've got a low E2 glass, which has a visible light transmission about 72% with the solar heat gain coefficient of 0.4. And then you've got other various products. In this case, we want to lower the solar heat gain coefficient, but then we lower the visible light transmission, as you see there with the triple silver low E, and about 60% visible light transmission, and about 0.27 solar heat gain. And so again, you see this trade-off between reducing your solar heat gain and then reducing the visible light transmission until you get all the way to the bottom. You see the reflective glass, which just a note on reflective, that was very popular back in the 70s and 80s, and we still see a lot of that glass today. And the idea was that it was seen as an energy-efficient product and solution to block out that solar heat and reduce the HVAC loads. The problem with that is you notice that the visible light transmission is only about 8%. So what you end up having are really dark and gloomy office spaces that have to run interior lighting. So whatever savings you're getting from your HVAC system, you have to weigh that against the cost of running your lights all that much longer. So you see that with all of these solutions, these are static plots. And whatever solution you choose, you're stuck with those attributes in terms of solar heat gain and visible light transmission. Now, to introduce the concept of dynamic performance, you see that glide path there where in the clear state, well, I should mention with dynamic glass, you can range that entire glide path of performance there. However, with standard dynamic glass, you have set points. So the set points that we have are along the visible light transmission scale here. You've got 60%, which is the clear state. And then when you apply a voltage to it, there are 3 intermediate states of 10. You've got 20%, which has a solar heat gain coefficient of approximately 0.17, and then 6% visible light transmission, which has a solar heat gain of about 0.1. And then on the very far end of the tinting spectrum, you have 1% visible light transmission, which you see there with the arrow, and 1%. It's important to mention that that is the level of visible light transmission that you need to achieve in order to effectively mitigate heat glare, and that has a solar heat gain coefficient of 0.09. So at that point, you're effectively blocking off about 91% of the solar heat in that tinted state. And again, to mention, it is when you apply a low voltage to that glass, that is what causes that level of tinting. When it's in a de-energized state, you have the glass in the clear state at that 60% visible light transmission. So we're going to show you some examples as we go on here with the next slide. This is a nice little illustration here that there's a reason your building has windows. And next slide. And it's not to showcase your beautiful blinds. Next slide. And it's to showcase the view and connection to the outdoors. And the idea here is that when this glass is in a clear state on this lake in Florida, the glare and heat is uncomfortable for the end user, but when it's tinted, then now you have a very crisp, clear connection to the outdoors and blocking out that heat, which is imperative in Florida. Okay, I think that completes one. We're going to go to, okay, I guess we got some more here. We'll just keep going. So another example from the Spirit Lake Casino in North Dakota. What was important with this slide is that as it goes through the cleared, because you can see that there's a lakefront view on the exterior of that window, which was a huge selling point for this casino. And the testimonial from the architect here is that dynamic glass allowed us to preserve the view and still perform as a vantage point with a prime lake view for the dining room. And the idea is that they had to control for that glare somehow, and if they had put up blinds or shade, then they would have lost that view. So again, another example of maintaining line of sight, right? Making spaces usable. Previously, before this was a skylight with dynamic glass, it was a regular low-E glass, and this is just a student dormitory in Ball State University. Previously, they had used just a low-E glass with a ceramic frit, but the glare and heat was too much of a problem, so they did a retrofit with dynamic glass and turned an unusable space and made it usable for the students here. Okay. Another example from not too far from here, the Kimmel Center for Performing Arts in Philadelphia, Pennsylvania. The beautiful barrel vaulted structure you see there, 150-foot tall barrel vaulted glass by Raphael Benoli, and they have these performing arts atrium inside the performing arts center here with these rooftop gardens on the top. And the idea was that they would have these gardens for events and for weddings, but because of the structure of this glass, the temperature rise was often up to 100 degrees Fahrenheit, so it was completely unrentable space. So the idea is that they came through and they came up with a solution. As you'll see, they actually reconfigured the entire rooftop garden and put up dynamic glass to create this beautiful wedding venue location. And it's important to note that the glass serves many functions. Not only does it block out that solar heat so that it's nice and comfortable, but you still maintain that crisp view of the skyline outside. So in terms of return on investment, the venue here saw improvement tenfold just in terms of increased bookings. So they went from 4 to 5 bookings a year to upwards of 40 to 50 a year. So really significant in terms of taking an unusable space and making it usable. All right. So again, I mentioned that 1% is important just to keep in mind. We have studies which show that anything greater than 1% will still create a glare problem. So when this technology was first being pioneered, we were experimenting with levels of 10 to 3 and 2%, but we found out that even at 2%, it was still a problem. But at 1%, the orb of the sun, obviously we wouldn't recommend looking at the orb of the sun, but it would not create a distraction for someone focusing on a primary task. So that's, again, why 1% is important when you consider a solar control or a glare or heat solution. Now we're going to talk about the zoning, which is important in order to strike the right balance, and that's what you're seeing here. So that ball bearing that represents the fulcrum, that's really striking the right balance between a glare control on the left and then energy, interior color rendering, and then daylight on the right. So I'll illustrate that through the next series of slides here. Starting off, well, this is an example here of a two-story atrium. And by leaving 10 to 15% of that glazing facade in the clear state, you're bringing enough daylight into the interior spaces so that it doesn't have that overly bluish aquarium sense to it. And this is really a great illustration of zoning. And essentially, zoning is creating bands of control, basically programming a preset number of rows of glass or groups of glass to be synchronized to tint however the end user chooses. And it's worth mentioning that this is completely customizable. In this case, the top 4 rows are programmed, and the next set of 3 are both programmed as well. Not in this picture, but that's how the end user chose to control the zoning in this case. As we move on, there's other examples where they've got the top portion of the glass there separated by a mullion. The top portion there is controlled by a zone, and the bottom IGU glass is its own zone. Okay? And now it's important to mention with our IGUs, we're able to have in-pane zoning. So instead of having the glass separated by a mullion within, so for example, if you have floor-to-ceiling glass, we can create up to 3 zones of control within that piece of glass. And we can do this through 2 methods. Either the first one is using a laser etching, where we essentially laser cut a part of that electrochromic coating to create separate circuits, which allow us to control the zone separately, which is what you see there in that illustration. And the second is adding a second or a third bus bar. Actually, if you don't mind going back real quick to the IG here. The second is creating a bus bar, which just runs in the middle of there. And what that does is it decreases your switching speed in half, or I should say, every additional bus bar added will decrease it by either a half or by 3 or up to 2 bus bars per IGU. And this is especially useful if you're talking about a skylight that's way up in the maybe 20 or 30 feet above people, where they're not going to notice the bus bar, but they want to have an increased switching speed. Okay, and then as we move forward, it looks like we're going to jump into part 2 here. Now we're going to talk about the aesthetics. We can move forward here. It's important to mention that the dynamic glass it's been on the market since 2003, and we've got our oldest installation is in Palm Springs, California, and so for 13 years, people have been using dynamic glass. It's just now beginning to ramp up a lot, but I'm going to go over just a few different case studies here and just show you how dynamic glass has been integrated with a design to achieve a certain goal. So in this case, in the Chabot College in Hayward, California, for those of you who don't know, Hayward is just outside of San Francisco. San Francisco is quite nice, about 50s, 60s degrees, but as you move inland, it gets pretty warm pretty quickly. Here in Hayward, it gets about 80 degrees most of the year. So in this case, the architect was trying to design a LEED platinum space as part of an addition to the school. And part of that design required an HVAC-free space. So the real challenge here, and you can see in this picture, is the exterior glazing. Originally, the architect was playing around with solutions of solar control through large external louvers or some other pattern to block out that heat. But there was nothing that could really compare to a dynamic glass solution, which is what the architect went for in this case, mainly because they wanted to preserve that view connection to the outdoors. But also, this dynamic glass was an enabler for that HVAC-free state. So, as you can see, in this, the floor acts as a cool source, and the ceiling has air scoops, which keeps a nice, cool ventilation through the space. And the dynamic glass, when it is tinted and activated, it reduces that peak demand that you would get during your peak demand hours for energy. And actually, by reducing that peak demand, you're able to have a viable HVAC-free space. So again, it simultaneously achieves daylight views, energy efficiency, and human thermal comfort. Another example from the Siemens wind turbine facility in Hutchinson, Kansas, where in this case the architect was more concerned about keeping a nice, crisp exterior look without employing large mechanical louvers or other solar control devices on the exterior. And so in this case, again, with that problem of heat and glare, as it's a southern-facing facade, there was no other solution that would really work other than dynamic glass to maintain the aesthetic that architect was going for. All right, next slide. This is an example from the TD Bank in Miami, Florida, where it was designed inspired by the Apple cubes, which were quite popular back in the early 2000s and 2010 or so. And it was kind of crazy to develop a glass cube in downtown Miami. But in order to do that, they looked at dynamic glass as a way of blocking out that heat. In fact, reducing that solar heat by over 90%. It allowed them to maintain this nice aesthetic and interior experience for their customers and their employees. This is an example from Colorado State University where this facade was facing west, and so when that sun was setting, it was quite harsh. And again, it created a nice environment for the students when that tent was activated, and then the solar heat and glare was no longer a problem for them. All right. This is an example from the Frost School of Music, and it's worth noting in this picture that one capability for these IGUs is that we can achieve any shape within a 5-foot by 10-foot IGU, in this case triangles. We can also do parallelograms, trapezoids. The only limitation is we cannot manufacture anything with a radius to it, and the glass cannot bevel or bow outward. But in this case, this just shows you a little bit of the design freedom that the architect went for. And just to give you some perspective on the size of the glass, the hypotenuse of those right triangles is 10 feet. So again, that was they were able to fit those triangles within a 5-foot by 10-foot IGU. But again, the idea is that the product and the technology has evolved to accommodate pretty much any imagination or creative design that an architect may have. And we'll see that with the next few examples here. Here's a great example, not too far from the area. Most of the people here are familiar with the U.S. Naval Academy. In this case, they employed the skylight, as you can see there, where it's pixelated. And in this case, they can actually simply control those zones as they're programmed and spell out "Go Navy" when they are playing during the Army-Navy game. And there's a dormitory to the left, so all the Navy midshipmen can look out the window and see that and get all excited as they face Army. So I'm an Army guy. I won't say any more on this one, so let's move forward. All right, another example from Seoul, South Korea. This is an example where they employed a skylight to achieve a culturally significant image there. And again, moving forward, another example where they've applied dynamic glass to an exterior sunshade in order to have a creative application so they can tint that sunshade when that sun becomes an issue. And that's in conjunction with standard low-E glass. All right. Now, it's important to talk about aesthetics here. Not all electrochromics are the same, and today we're still pioneering the technology, and it's improving more and more. On the left, I'm going to show you some of the first generation electrochromics, and then on the right, it's going to show you where we are today, and in fact, where we're improving on this even further. But in the clear state, let's actually go back for a second. In the clear state, you can obviously pick out which 8 IGUs are that Generation 1 glass. And you've got those bronzy, reddish, yellowish-looking pieces of glass there. Yep, exactly right there. And that sticks out compared to your standard low-E glass. However, where we are today, on the right, you've got the much crisper, clearer aesthetic, which is something that we've improved on. And then when we go to the tinted state in the next slide, you can see that before, when it was tinted, you had this real dark, almost a black hole effect, which did not really achieve the aesthetic we were going for. But now, in Generation 2, you've got a much clearer, crisper, neutral reflection that is much more in line with modern architectural edifice. All right? And I'm just going to show you some examples in the clear state. This is from Cedar Rapids, Iowa, you can see there. And another example from Los Angeles, California, the Lantern Group in the clear state. And then in the tinted state, this is again the Frost School of Music from those triangles that you saw earlier. From the exterior, nice neutral reflection here's an example from the Excel River Center in St. Paul, Minneapolis, the IGU portion being in the top there. And again, from Mercy Orthopedic Hospital in Fort Smith, Arkansas. And then the next slide is going to show you, well, I guess in this one it just shows you the tinted state. But you see that it has, and we can't build this as a privacy glass, but when the glass is in the tinted state, you can see that it has a real reflection as if it were a reflective glass itself. And the reason is that we've improved on the optical tuning layer from Generation 1 to Generation 2. So this is an example from the Boston Museum of Science. What it's showing you is that there are different zones of control on this large glass facade here. And as we go to the next slide, I believe it will show you from the interior. So here's a split shot or split screen of the interior from the left and then the exterior on the right. On the left, there's actually two zones of tint being control. On the bottom, that's actually 20%. And then on the top, you've got the 1% visible light transmission on the left there. But then as you look on the right, depending on what, it doesn't matter what level of tint you're achieving, you see a nice uniformity, so you don't have almost a checkerboard fashion of aesthetics. As long as it's in any one of the three tinted states, you're going to have a nice uniformity, and you can't really tell what level of tint those zones are at from the outside. However, you can definitely tell on the inside that there are different zones of tinting there. All right, and just on the same line of aesthetics, it's worth mentioning that from the interior perspective, the hue is going to be in the blue, as you've seen that blue hue. And the reason for that is the technology as it's been developed, when that electrochromic coating is energized and when the solar light comes through, the light falls on the visible spectrum and it peaks in that blue portion of the visible spectrum. And that's just the characteristic of the glass. However, from the exterior, we can have a variety of outboard color options which are complementary to the aesthetic that you may have for your particular project. So the four standard colors that we have are clear, blue, green, and gray. And then in this case, there are custom colors available, and you can see here on the left, in the Minneapolis-St. Paul Airport, they have an evergreen motif aesthetic going already, so they were able to match dynamic glass with an evergreen exterior hue and get in line with the current characteristics of the airport. All right, next slide. Another application, I'm just going to show you a few applications here. This is one example of historic preservation at the St. Johnsbury Athenaeum in Vermont, where they actually had a skylight that was standard loaded glass, and they had to periodically whitewash it to preserve the artifacts on the inside. And it was a cumbersome process. It required a lot of maintenance. But they were able to, when the architects found out about dynamic glass, they actually did a retrofit on that skylight, and they put in dynamic glass, and it was a triple pane glass, so it provided the proper level of UV protection, and it achieved a nice interior color rendering, which is important for the curator. And in this particular example, they had a wonderful monumental painting by Bierstadt of the domes of Yosemite, which I believe there's some other works of Bierstadt as well at the American National Gallery. But again, this is an application where they employed electrochromic glass to preserve artwork. And going forward, there's another example of the Boston Museum of Science. We've already covered this one, but we're seeing a growing trend of incorporating dynamic glass with cultural, institutional to enhance the creative and thought-provoking spaces here. And, okay, moving on. One option here is, we know that retrofits are a common task that we have, especially when we're talking about upgrading buildings. And so in order to minimize the cost of pulling out or installing wires and knocking down walls, we can actually do retrofits through wireless installation. So by that I mean we can actually install IGUs that have a photovoltaic cell on the outside with a battery pack on the inside, and that's what you see there in that picture, so that you're not actually installing any wires to a centralized location. It's all done via wireless control. And then it's important to note that on a full charge with that PV, you can actually have up to 5 days of IGU life before it needs to be recharged again. And so the idea is that you can actually have all the interface of a wired control, but you can actually have an app like on a smartphone or iPad or an Android that would control it and gives some sort of centralized, either a DMS manager or the end user control over their glass with an iPad app. Okay. Now, as we talk about the cost comparison, this always comes up. I want to just kind of illustrate, trying to get to an apples-to-apples comparison here. So on the right, we'll start off with a dynamic glass solution, where there's just one cost consideration, which is dynamic glass. But it's important to note that one of the intangible values here is that connection to the outdoors that you really can't have with any sort of blinds or shades. So right off the bat, if maintaining a view and connection to the outdoors is important, and here in D.C., maybe you've got a building that has a view of the National Mall or some sort of monument, there's really no comparison to direct line of sight to that view that comes with blinds and shades. So on the left, you have a conventional solution with regular glass, and in this case, they've opted for blinds, and there's an external sunshade. There's an increase in their HVAC load as well as unsynchronized lighting. So there's a lot of ulterior factors that go into a standard solution. And again, it's worth mentioning that this is only an apples-to-apples comparison if you're trying to control for that heat and glare while maintaining a view and connection to the outdoors and optimize daylighting. So keep this picture in mind, and then we go to the next slide. I want to illustrate just a graphic here which illustrates the impact on building operation costs. So what you see there with that building on the left is that 90% of typical building operation costs are associated with people, either through staffing, salaries, workforce, benefits, and 9% of that is rental costs, and then 1% is actual energy costs. And the idea is that if you were to have a 10% variation with all three of those categories, you see there in that plus or minus energy costs, you've got only 0.1%, which is quite small. When you get up to your staffing costs with a 10% variation, you're talking 9%. So you can see the magnitude here of small differences with your staff and people costs versus your energy costs. Much, much greater when you're talking about people. And the idea here is that a happy, healthy workforce is a component of a productive, successful business in the long term. And this is all coming from the World Green Building Council, the well building standards. There's this real revolution in terms of considering people as a measure of return on investment. So when we go back to that apples-to-apples comparison in the next slide, you can see, forward here, this is showing you an example of the dynamic glazing solution compared to a static solution. In this case, they're also employing the cost of sunshades, auto interior blinds, and the differentiation per square foot comes to $1 in this case. And with the energy payback, and this is strictly a scenario-based example, we're talking about a 5% improvement of efficiency with dynamic glazing, and we're saying that that's because of the synchronized HVAC system, which is reducing the dynamic glass is reducing the peak demand, so the HVAC isn't running nearly as hard. And then if you have a smart lighting system integrated with that through either Lutron or Siemens or some other company, you can actually you can incorporate dynamic glass into a smart integrated system to improve energy efficiency. And in this case, we're talking about a return on investment in only 1.3 years. But in terms of the human capital payback, mean you no longer have people that have a glare or heat problem. They're more focused on their primary task. They've got that connection to the outdoors. They may feel more connected to their workplace than, that's what we're getting at when we quantify the 1% improvement. You're seeing a return on investment in terms of less than 1 month, as an example here. So now as we go forward to another example, which has just dynamic glass compared to a much slower solution of static glass and manual shades, you can see it's about a 2-to-1 ratio here in terms of difference per cost per square foot. So your energy payback is much longer, as we're talking about a 20% improvement, because the dynamic glass will be just that much more energy efficient if you're dealing in this scenario here. But your return on investment is around 18 years in this example. But now with your human capital payback, we're looking at a 2% improvement, and your return on investment will happen in about 1.8 years. So this is just a strictly scenario-based example, and it's worth mentioning that a big question that we get asked a lot is, well, how much exactly are we going to improve efficiency by going with the dynamic glass solution? And that's a very valid question, and there's a lot of factors that go into that. The footprint of the building makes a huge difference. How much floor-to-ceiling ratio there is, how much glass, and if it's facing east, west, or south. All those factors get put into consideration when we start looking at how much more efficient we will make a given space. So it really is on a case-by-case basis, but this is certainly something that I'd be glad to work with anyone who has a specific project in mind, or any questions. We can talk certainly about that afterwards. Okay, next slide here. So I'm not quite sure how this is going to work here, but let's go forward and I'll explain in a little bit more detail, a little bit more of the technology. Okay, well, it looks like some of the slides didn't get in here, which is fine, but at this point, I'll do the best I can to answer any questions in the next 10 minutes. Again, I wish I had the visual. Here we go. All right. I'll run through these, and then again, if there's any issues, we'll move forward here. So just to give you an example of how the glass works, I'm going to orient you to this cross-section here, starting on the outside and working our way in. So on the right side, you see that cross-section of an IGU. Think of it as like a glass sandwich, if you will. Surface 1 faces the outside, so you've got surface 1 and 2 is the surface for that 4mm support light, which is the heat-strengthened glass. And so that heat-strengthened glass is actually laminated to what we call the device light, which actually has it's the annealed glass, the 2.2mm coated light, annealed glass that has the electrochromic coating on it. So surface 2 and 3 are laminated together. Surface 4 has that electrochromic coating, which faces the interior airspace, which could either be filled with air, krypton, or argon, depending on the specifications for the project. Surface 5 and 6 show you that is the 6mm matching heat-strengthened light. Now, this is just an illustration of the standard Sage product that we have. However, it's worth mentioning that we can specify the glass depending on whatever standards you have. So in this example, it's a 1-inch industry standard, but we can go 1.5, 2 inches, up to 3 inches. We can do triple pane. We can do blast proofing, bullet proofing, hurricane strength rated. We also consider wind and snow loads. So all these examples have more or less been the standard Sage product, but just keep in mind that this is highly versatile, and it can pretty much, if any regular IGU glass can accomplish this, then we can do that as well. So, okay, let's see here. This is just showing, I don't know if the other slide was showing you here, but this is just illustrating a little bit up close and personal about how that electrochromic coating works. It's worth mentioning that the actual electrochromic portion on that annealed glass is less than the width of a human hair, so we're talking microns thin. And it's essentially 5 layers of coating, and it's in this case it's lithium ions, which are rearranging themselves. So I don't think it shows you in this picture here, but this is showing you in the tinted state that those lithium ions, when they're energized at low voltage, they rearrange themselves to go from coating 2 to coating 4 layer. And that's what creates that tint, that's what creates that blue hue. It's that rearrangement of the lithium ions through that conductive, translucent conductive coating there. And that's essentially what that electrochromic coating is all about. What this is showing you, and this is a slide that needs to be updated, but comparing single pane clear to the ASHRAE standard, this is showing you the percentage of annual energy savings and also the percentage of peak demand reduction. So when this was published in 2010, the studies from Palladino and Co. But looking at the DC example, the idea is that when you compare electrochromic double pane glass to single pane clear, you're looking at the 45% reduction or annual energy savings and 35% in peak demand reduction. And then when you compare it to the ASHRAE standard, a little bit less, 22% in DC percent annual energy savings, 18% with the peak demand reduction. And then when you compare electrochromic triple pane, you compare it to single pane clear, then you're talking about 53% saving. And again, with ASHRAE and static triple, you can see that the energy savings are range anywhere from 18 up to 34% in this case. All right. Now this is just an illustration of how the system works here. Starting with the electrochromic glass IGUs there, you see that every IGU has a connector, and it routes through a 4-conductor cable, low voltage system, into a terminal box. Now this is just one standard example. Depending on the size and scope of the project, you may not need a terminal box. It may just go directly to an output panel. But in this case, if we're running multiple IGUs over a distance of about 150 feet, then those IGUs will be routed to a terminal box. And then that terminal box also picks up an exterior lighted sensor. So one question we get asked is, well, how does it work? Is it an automatic process, or is it, does it have a manual override? And the answer is it has both. So the exterior light sensor, we have pairs of sensors per set of IGUs. A high-angle sensor and a low-angle sensor, which detects when the sun is setting, that low-angle sensor will pick up that light. But then when the sun is high up in the sky, that high-angle sensor will then pick up that lux level. And so that's what controls the automatic tinting and clearing of the glass throughout the day. And then that is routed to a central output panel, which again, it's worth noting that if you have a BMS system, this can be integrated with a BMS system. This also has smart chip technology so that you can route the signal from an iPad or an iPhone app. This is where it'll go into this output panel and control the override system that way. And then you also see the wall switch, which feeds directly into the output panel as an override as well. So those are the two means of override in this one example. That's completely customizable depending on the project. Okay? Okay, so this just covers what I just went over here. That you've got essentially got an automation system. You've got an automatic. It can work automatically, or you can have the manual override or the mobile application. So completely customizable depending on the needs of the end user. All right. So it's just showing you as the sun moves. Well, it probably won't show you, but the idea is that as the sun moves throughout the sky, the glass will tint accordingly. In-pane zoning, which we've already covered. I think the rest of the slides should be pretty. Actually, I think at this point we've pretty much covered everything. And for the sake of time, looks like we've got about 4 minutes left. We can take a few questions if there's any out there. Does that work for you, Eric?
Yes, it does. I was just about to suggest something along those lines. Folks, if there's a text box on the right-hand side of the screen, at the bottom of that column, there's a place where you can type in your question and hit the send button. They'll scroll up in the white area above. I'll then read them to Chris and let him answer them. Don't be alarmed if I skip over a question, because I might try to group some questions together that are similar or to go on with a particular train of thought. So I invite everybody who has a curious mind to start typing in their questions there, and we can take a few minutes here to get what answers we can. I had a question. You mentioned before the intermediate bus bars, or what they were, that would reduce the switching time. What kind of factors of time are we looking at in terms of when you change from one state to another? How long does it take a regular, fairly large size window to transition?
Right, that's a great question. And what I like to do is when I give these presentations is have an example of a sample piece in front of me. Typically what we say is it takes about anywhere from 10 to 15 minutes to go from the completely clear to the completely tinted state. So it's not an instantaneous change. However, that's such a general term because there's a lot of factors that go into the switching speed of the glass. Temperature. When it's warmer, both inside and outside, you're going to get a much quicker switching speed. As you'd imagine, with heat comes a quicker flow of electrons. When it's colder, you're going to have a slower switching speed. Depending on the size of the IGU, if it's a larger IGU and there's no bus bar, then it could take maybe, and it's a cold day, you could see maybe 15 minutes to 20 minutes. Now that's going from completely clear to the completely tinted state. To go from the completely clear state to start noticing a tint, it takes, I would say, probably 2 to 3 minutes, and then you'll start to see a noticeable difference. Now, the idea is that it's preferable not to have an instantaneous effect, but rather a real gradual tint, because the idea is that we don't want the end user to have that jarring experience. I always use the example of leaving a movie theater and going out to the bright sun. It's an immediate switch from dark to clear. But the idea is that it happens gradually without really being noticed unless you're cognizant of that. And then, like I said, in about 2 to 3 minutes, you'll begin to see a tint. Now, it's not uniform while it's in the transition stage. And you'll see that there's variation. It kind of has waves, or it's going to be kind of gradually filling in. But once it reaches those set points of 20%, 6%, and 1%, you will then have complete uniformity. So I hope that answers your question there.
Yeah, so basically the strategy, operational strategy would be, as the sun moves over to the west facade to set, it gradually would taper in the tinting to prevent that, that late afternoon glare.
Exactly.
Right, but it would not be something where, like with skylights, that we have dimming systems on our incandescent lights, not incandescent, what do you call them, electric lights, so that, if a cloud passes over, they bring up the lights, and if the cloud goes away, then so you're not kind of responding that dynamically to like passing clouds, you're responding to the presence of light, not the presence of shade. So it's kind of an opposite way of thinking.
Right, right, exactly.
Oh, go ahead.
Oh, yeah, exactly. So when you have conditions of, partly cloudy skies where the sun is being obscured and then revealed, your glass is going to, it's set to pick up certain levels of pre-programmed lux. But once it has that set point of lux, then it's going to respond accordingly. So, yeah, you're exactly right. It's not going to switch that quickly.
Okay. Well, we're a little bit just going over the hour here, so I put your websites back on the screen. I'll leave that up for people. Also, folks online, you can hit that down arrow icon in the lower left corner of that center area where the slides are if you want to download the presentation, so you can capture all these websites if you don't have the time to write them all down now. I'll leave this page up a little bit so that people can do that. Once again, Chris, thank you very much. Sorry for our technical difficulties, but thank you for bringing us all this information today, and it sounds like a very dynamic product.
Excellent. Thank you so much for everyone's attention.